We're going to now evaluate an area under a curve using U substitution. And if we did not know what we were doing, or if there's anything different, you'd probably still get the right answer. Okay? So we know, first of all, to find an area under a curve, you must take the antiderivative first. You can't plug in the 2 and then the 0. Don't forget to take the antiderivative. Okay, but I can't take this antiderivative just by looking at it. I'm going to have to use U substitution. So I set U equal to the inside of my composition. Take the derivative du is equal to 2x dx. dx is 1 over 2x du. All right, now I'm not going to worry about these numbers right now. I'm just going to worry about taking the antiderivative. So I have x root u 1 over 2x du. Okay? U replaced x squared plus 2, and dx was replaced by 1 over 2x du. Okay? I can see that the x's will cancel. I can take the antiderivative of root u times a half. Be u to the 3/2 times 2/3 times a half. So that's 1/3 plus a c. And we know that we can replace the u with x squared plus 2. But that's not the answer, because this is a definite integral. So the answer is the change in my antiderivative, right? That would be the exact area under a curve. And I'm going to go ahead and at the end place a straight line saying I'm going to find the change between 0 and 2. And I can do that. And I'd have 6, 1/3 6 to the 3/2 minus 1/3 2 to the 3/2. Okay, and that's as simple as I can get the answer. Maybe I can factor out a 1/3 or something, but that's it. Okay, you probably would have guessed to do this and you would have gotten it right. We're good. So what's different about this? Why did we even have to bring it up? Because in the middle, here and here, if I use the numbers 0 and 2 just as like a placeholder, and if I use the numbers 0 and 2 here kind of like a placeholder, these are wrong. That's wrong, and that's wrong. Why are those wrong? Well, I have dx here. Dx means a very small change in the x-axis. What is an integral? It's an infinite sum when it's in this form, a definite integral. It's infinite sum of heights of rectangles times widths. This width is a small change in the x-axis. These numbers give us our boundary. These are x's from an x-coordinate of 0 to an x-coordinate of 2. When I switch from dx to du, I switch the axis in which my graph is kind of placed on top of. And that means these numbers 0 and 2, which are x's, can't be used if I have a du or if I have a u. So the integral and this need u's. Now, you discuss with your neighbor what we would put instead of 0 and 2. Figure it out. Okay, I'm going from 0 to 2 on an x-axis. That's equivalent to what on a u-axis? Anybody have any ideas? Tricky, right? 2, 0? No. Mr. Stringer, what do you think?
So I think you would
Yep. So if I have an x of 0, what's that equivalent to in terms of a u? 2. If I have an x of 2, what's equivalent to that in terms of a u? 6, right? Now, how did I get that? Because I have this right here. This is the relationship between the x-axis and the u-axis for this problem. So whatever you set u equal to, you can plug the x's into that, and you will get u's. No? This answer is still correct, but I'll show you another way to get the same answer. We'll get there. So you might be thinking, okay, great, Mr. Master, but we still got the correct answer, just not even worrying about changing what we call the bases. This is called the change in base. We still got the same answer. Why do I even have to worry about this? Well, maybe you want to do the arithmetic a little bit earlier, and maybe you want to get our answer a little bit earlier. Instead of plugging back in the x squared plus 2 into u, watch, if I plug in 6 here, and then I subtract 2 plugged in, I get the same answer that I got after the step of plugging the u back in. Okay, so I could have just like stopped here, not done any of this, and gotten the same answer. 1/3 6 to the 3 halves minus 1/3 2 to the 3 halves. Same answer. Okay, so maybe you want to do that. But you're still probably thinking, well, Mr. Messer, that's great and all. However, like, I'm probably going to go back to x's anyway. I feel more comfortable with x's. Why would I have to do that? Well, there will be certain problems where you are required to change your bases. Okay, here's a type of problem that you will see. We have an integral from 4 to 9 of f of 2x dx, and that's equal to 6. The question is, what would be the equivalent definite integral using f of u instead of f of 2x? So this is like a multiple choice problem, and you see all the answer choices look like this. It's a definite integral. It's f of u du. And we got a number here, a number here, and a number here that are different in all of the answer choices. You guys try to figure out what those 3 numbers are if I have an integral with f of u du instead of f of 2x dx. Now pause, discuss with your neighbor what you are setting u equal to and what you are doing. Go. Discuss first and then work. All right, so we set u equal to 2x, and because of that, if x is 4, u must be 8. And if x is 9, u must be 18. Fantastic. These numbers must be 8 and 18. But then students say, all right, well, I did it. This is 6. Circle this answer, and they get the problem wrong. Okay? Figure out why 8 to 18 of f of u du equals 6 is wrong. Go. No, not like that. Yes, but not because you're changing that to a u. That's an area. That's an area. It's not an x. When you guys did your quiz, did you just stop here? Did you say u equals 2x? Great. Okay, next question. What did you do? Yeah, you took the derivative. You substituted it in. Go ahead and do that process for this as well. When you change dx to du, it doesn't just change, it becomes 1/2 du. So I have this half in here, which I can pull out and then multiply both sides by 2. So this becomes 12. And that's the correct answer. Okay? So that is why you must change your bases for a question like this. The other two examples that we skipped, you don't have to. As long as you go back to x's, you can go and find the change in the antiderivative from 0 to pi over 2 if you went back to x's. If you stop at u's, though, change it to the u's. Let's do another one like that where you're just forced to write a definite integral with du. So I want you to figure out what goes here, which is a number, which goes here, which is a number, and then what the correct inside of the integral is. And u is equal to root x. I'm telling you that. Yeah, it seems like it. Do we put a u in 2 places? Am I only going to put it in 1 place? For this problem, it's kind of funky. We first know that we change it to 1 to 2. Let's go ahead and substitute in u for the root x's in both locations. And then I replace the dx with 2 root x, du. Anybody else do it this way? Substitute in u in 2 spots, and then you substitute in 2 root x. Now, if we look at it this way, we might seem confused. We see a u and an x, and you're like, I should just have u's. But if we just remember that u is equal to root x, it's actually these that cancel. And if you wanted to, you could have kept this as root x and see that they cancel. Or you change this to a u, see that it cancels. There's different ways to do it. But since u equals root x, these go away. And now I have my integral 1 to 2 of 2 e to the u. Okay? Well, let's say I wanted to find this. I'd have to take the antiderivative of 2 e to the u. We have not talked about the antiderivative of e to the x. Well, first let's discuss the derivative of e to the x with your neighbor, and also discuss the derivative of e to the kx with your neighbor. Okay, ready, set, go. What is the derivative of e to the x, and what is the derivative of e to the kx? Okay, if the derivative of e to the x is e to the x, the derivative of e to the x is e to the x, right? It's its own tangent slope producer. Well, do I use the power rule for e to the x and make it e to the x plus 1 times 1 over x plus 1? No. What's the antiderivative of e to the x? Just e to the x. Such confidence exuding from all of you guys. Now, this one, a little tricky. What if I have a constant in front of x? You guys discuss with your neighbors what the antiderivative of e to the kx is.
1 over k.
Good. We need this 1 over k to cancel with the k that pops up in its derivative. This is the whole multiply by the reciprocal of the coefficient of x to the first power that we talked about last class before we got into the U substitution grand technique. Okay, now, does it matter if it's e to the 3x or e to the 3x plus 1 or e to the 3x plus 5? If it's x to the first power, all you need is the reciprocal of the coefficient of x. The coefficient of x is the value that comes before x. Not, you're going to take 1 over 3x plus 1. I'm just taking 3. And I have 1 over 3 times e to the 3x plus 1. Okay, this can be done using U substitution. We'll talk about it in a second with this problem. But before I get to that problem, if I go to this bottom right problem, I could do this problem without using U substitution. Good, Mr. Lamaro. I would start by rewriting this as the antiderivative of e to the negative x. Now you discuss with your neighbors and write down the antiderivative of e to the negative x. It actually is the exact same as the derivative of e to the negative x. Because you're multiplying by the reciprocal of the coefficient of x, the reciprocal of -1 is just -1, so that doesn't change much, okay? But the other two here involve U substitution. Now I said, step 1, set U equal to g of x. G of x is typically the inside of the composition. Discuss with your neighbors what you would set U equal to in this case. A number is wrong. Negative x squared is u. Why? How do you write that? It's e to a power, right? That's the composition. The parentheses kind of are around the power. When we took the derivative of e to the negative x squared, remember we would say, okay, if I'm taking the derivative of this, I would start by taking the derivative of e to the power and then multiply that by the derivative of the power. So it's the power that is going to be what u is equal to in these situations, typically. Let's say u equal to negative x squared, du is negative 2x dx. dx is negative 1 over 2x du. Let's see what happens. I have 5x e to the u, negative 1 over 2x du. The x's will cancel. Don't forget to take the antiderivative. However, for this, the antiderivative is just itself. So the antiderivative of this is negative 5 halves e to the u plus c. Finish it off by replacing what u is equal to. Okay, you guys do the one on the bottom left, please. You get negative e to the 1 over x plus c. All right. All right, curveball. Who remembers? If I had a piece of candy, I'd give it to you if you got this right. The derivative of 5 to the x. Five times the natural log of 5 to the x. No. Good try, though. That is correct. Very nice, Mr. Miller. 5 to the x ln 5 is the correct derivative of 5 to the x. Do you guys remember that? No, because we probably saw it once on the derivative rules lesson involving e to the power in this, and then we haven't dealt with it. But now, and I have seen this on an AP test, tell me what the antiderivative of 5 to the x is. Discuss with your neighbors. Figure it out with your neighbors. All right. Mr. Amberg got it correct. It's 5 to the x over ln 5, or times 1 over ln 5. That's the whole multiply kind of by the reciprocal of the coefficient. In this case, there's not really a coefficient, but we have to realize that its derivative has this extra ln 5, so I need to be able to cancel that. Cool. All right, moving on. Let's talk about the antiderivative of 1 over x. In your notes, it was already written as x to the negative first, right? You guys already have that, but we know that that's the same as the antiderivative of 1 over x. Okay? Now, if I asked you to take the antiderivative of, say, x to the negative second, which is the same as 1 over x squared, you guys could do that, right? We add 1 to our power, multiply by the reciprocal. I'd write that as negative 1 over x, right? Well, you guys do that with 1 over x. Seems like we've done it before, right? If I know I've done 1 over x squared, I've probably done 1 over x. So x to the negative first, go ahead and use the power rule. What would be the antiderivative of 1 over x using the power rule? Well, so I add 1 and I get x to the 0, and then I multiply by the reciprocal. I guess it's 1 over 0 x to the 0 plus c. So it's like, okay, well, I guess 1 over x doesn't have an antiderivative, or it doesn't exist, or it's 1, or it's 0, I don't know. But this is not true, okay? The power rule does not work for x to the negative first. It works for every other exponent of x, fractions, negative 2s, any negative value, any positive value. It works for every other one except for x to the negative first. So write that down. Power rule does not work. But there is an antiderivative of x to the negative first. And if we flip over, and if I asked you what the derivative of the log function is, you would tell me that it's 1 over x. Which means the antiderivative of 1 over x must be log x. It's different. Plus c, right? And that's great, but it's a little more complicated than that. Because the log function, and if I started with asking you, what's the derivative of log x? You're automatically kind of confining yourself to the positive x's. Because the log function does not exist for any x that is less than or equal to 0. This is what the log function looks like. It's the exponentially slow growing function. So when you say, hey, the derivative of log x is 1 over x, that's correct. However, you're really only talking about the positive half of 1 over x. Okay, so if I ask you what is the antiderivative of 1 over x for the positive x's, yes, you could answer it this way. It's log x. However, let's say I started with this question. What is the antiderivative of 1 over x? I started with 1 over x. Well, 1 over x is not constrained to the positive x's. 1 over x lives everywhere except for at 0. It's got that piece and this piece. So I can kind of trace over this guy in green as well. Okay. Well, now I can't just answer log x because log x is only positive for its x's. I need to expand the graph of log x so that I have not only this piece over here, but a piece over here whose derivatives will be given by 1 over x. It turns out that piece is the log of absolute x. So now that I have an absolute value, I have expanded the domain of the log function so that I have x's that can be positive and negative plus a c. And if I ask you what is the derivative of log absolute x, you are automatically thinking of any x that you could use, and the answer would be 1 over x, but the entire graph of 1 over x. Okay? So what are we taking away from this? If you start with 1 over x and they do not constrain your domain, you must use an absolute value. Whereas we didn't really worry about absolute values the first time we talked about logs. Okay? So the antiderivative of 1 over x is log absolute x. Cool. Now, we got 1 over kx. I'm going to ask you a question. What is the derivative of log kx? One over kx times k. So it's just 1 over x. How do I take the derivative of log of kx? The outside is the log, the derivative is 1 over, the inside is kx, so I got k as its derivative. Okay, so this antiderivative is not as simple as just saying it's log absolute kx. That's wrong. Okay, I need that 1 over k. There are 2 ways we can do this. Okay, here are my 2 answers. The first way I could do it is splitting it up. And I could have integral of 1 over k times 1 over x dx. And if I take this, well, the 1 over k is just a constant. The antiderivative of 1 over x is log absolute x. And boom, this is a function whose derivative is 1 over kx. I just split this up into 2 different fractions. 1 over k is a constant. If I have the antiderivative of a constant times any function, we could leave the constant, multiply by the antiderivative of the function. Okay? Or I can multiply by the reciprocal of the coefficient. Similar to like e to the 3x, I need 1/3 e to the 3x. I could write this and say, okay, if I'm thinking about the antiderivative of 1 over x, that's log absolute x, but the x is kx, but I need a 1 over k in front of it. This also gives you a function. This is a function whose derivative is 1 over kx. Okay, because this derivative is 1 over kx times k. Boom, boom, k's cancel. I have this 1 over k in front of it, so that works. Here, I have 1 over k times 1 over x. This works as well. So it kind of shows you logs are kind of interesting in terms of its growth, multiples of things. There's multiple answers. Okay, antiderivatives are interesting in that you can have multiple functions whose antiderivative is what you're looking for. Okay. So 3 over 5x. 2 answers you could provide. You could either say, oh, that's just 3 over 5 times 1 over x. And its antiderivative 3/5 log absolute x plus the c. Okay, that's one answer. Or you could say, all right, I got the 3. I got the log absolute 5x because it's just x to the first power and I just have a coefficient of 5. And multiply that by 1/5. This is also correct. Now the next one looks like a simplify first problem, and it is. We simplify this to be x plus 1 over x. However, for x you use the power rule, and let's no, we're good. For x you use the power rule. The antiderivative is x squared over 2. But for 1 over x you do not. Log absolute x plus the c. Now it doesn't matter if it's 5x or if it's 5x plus 3 or if it's 5x plus 7. Like these, doesn't matter that I have 4x minus 1 or 5 minus x. It's still x to the first power. So you see that x to the first power, you think, okay, the coefficient of x is 4. I need to multiply by the reciprocal of the coefficient, and this would be the correct answer. You could use U substitution to discover this and to get this answer. However, it's easier to just kind of figure it out. Think about the derivative of log of 4x minus 1. It would be 1 over 4x minus 1 times 4. You need the 1/4 to cancel with the 4. This guy, figure this one out. You have a negative 2x, right? All right. Keep it as negative 2x. Close. The coefficient is negative 2, so I need a negative 1/2 log absolute 5 minus 2x plus a c. Okay, these are ones I don't want you to use U substitution for, but I want you to recognize that x has something where if you took the derivative of it, you need to multiply by that coefficient. So this would be 1 over 5 minus 2x times negative 2. The negative 2 comes from the derivative of the inside. So I need this negative 1/2 in front of it. So I don't want to use U substitution there, but I do need to use U substitution elsewhere, like this situation. Mr. Messer. Okay. Yes. Okay. No, we're at a study hall. Students are permitted and encouraged to see their teachers after school and then bring a note to me that they were with a teacher. So Thursday he should go to tutoring. Tuesday we have practice, but he should go to tutoring and then come to practice after he's done with tutoring. Okay, will do. I'll talk to him. Okay, thank you. Okay, so here's a situation where we need to put your phone away, Mr. Amber, where we need to recognize that the numerator is a derivative of the denominator. If I ever see this situation where the numerator is a version of the derivative of the denominator, set u equal to the denominator. Let me show you why that works out. Du is 2x dx. dx is 1 over 2x du. This turns into the antiderivative. The x stays divided by, this becomes a u. This is 1 over 2x du. The x's cancel. Notice, I just have 1 over 2u. Two ways to write the antiderivative. Whichever way works for you. You can either have 1/2 log absolute u plus c, or 1/2 log absolute 2u plus a c. It doesn't matter. And that's the same as 1/2 log absolute to x squared plus 1 plus c, or 1/2 log absolute 2 x plus 1 plus c. How are those the same answers? You know, that's the question. Because look at the derivative of log of 2x. The derivative is 1 over 2x times 2. The 2's cancel. So it doesn't matter if I have a constant in it. The derivative of the log of some kx is just 1 over x. Okay? Now, I'll show these on the video, but go down to this guy, the last problem. 1 over x squared. You're going to do your homework. You're going to use a lot of logs. You're going to be like, okay, I'm on top of this. And then you're going to see this problem on a quiz or on a test, and you're going to think to do this. You are wrong if you do that. This is wrong. Okay? The power rule works for every single power except for a -1. So, don't forget this moving forward, that this can be rewritten as this, and the power rule does work for this. That's the antiderivative. It's only for x to the first in the denominator. All right, watch the rest of the video for the other examples. I haven't stopped it yet. I'm going to keep going.
I still get this after school and I'm going to go grab that.
All right, so for this example, the key is when you take the derivative of x cubed plus x, we're used to not multiple things, just like 3x squared. We're not going to subtract the 3x squared to solve for dx. This is actually a product of 3x squared plus 1 times dx. So when you solve, the entire thing goes in the denominator. Okay, so let's see another one. I believe you see this on your homework. You think e's, so you think, oh, set u equal to x, but no. It's actually the denominator, u is equal to 1 plus e to the x. The version of the derivative is in the numerator. So this works out so that the e to the x in the numerator cancels with this 1 over e to the x. When I replace dx, I have the antiderivative of e to the x. That's not u, but 1 plus e to the x is u. I have 1 over e to the x here. These cancel. The antiderivative is log absolute u, which is log absolute 1 plus e to the x plus c. Same deal with this guy. Set u is equal to tangent, and you will find that the secant squareds cancel, and your answer is log absolute tan x plus c. Bringing us to an interesting antiderivative, the antiderivative of tangent. We look at tangent, and it seems like there should be some easy function whose derivative is tangent, because like sine with cosine, you know, sometimes the trig functions work well with each other. But it turns out no, but we can now find the antiderivative of tangent. I start by rewriting it as sine x over cos x. And I notice that the numerator is a version of the derivative of the denominator. I'm going to set u equal to the cosine of x, the denominator. And watch what happens. I got negative sine x dx. I solve for dx. I have negative 1 over sine x du. I go ahead and replace cos x with a u, replace dx with negative 1 over sine x dx, du, and the signs cancel. And I'm just left with the antiderivative of negative 1 over u. Its antiderivative would be negative log absolute u. Or, and here's the antiderivative of tangent that we did not know until now, negative log absolute cos x plus c. Who knew? Okay. We can do this with a definite integral. This one is tricky because usually you're like, okay, I'm looking for the numerator version of the derivative of the denominator. Well, the denominator is a product, so you have to use the product rule. It's not going to cancel with anything. But then I think, what if this x was x to the negative first up there? And then I think, oh, the derivative of log x is x to the negative first, is 1 over x. Because of that, I will set u equal to that log x. And du is 1 over x dx. dx is x du. Watch what happens. I'm going to turn that back into 1 over x. This is u. This is x du. The x's will cancel. I can take the antiderivative. Let's actually just use u's here. Why don't I just go and use the u-axis. If x is e, u is the log of e, which is 1. If x is e squared, u is equal to the log of e squared, which is 2. So this can be a 1 and a 2. Antiderivative of this would be log absolute u from 1 to 2. And I can find that easily. Log absolute 2, which is the log 2, minus the log absolute 1, log of 1. Log of 1 is just 0. Remember, 1 can be written as e to the 0, so this is just 0. So my answer is log 2. Okay? That's it.